Hey everybody, welcome to 5D2's video. We're going to be using the things that we've learned about sine, cosine, and tangent, specifically sine here as we start with the Explore, to do some problem solving with trigonometry. So one of the things that we can do is to derive a new area formula. Now you say, Mrs. Pollack, of course, with an area formula with a triangle, it's just base times height. Well, that's true, but this is a formula that we can use when we know information in a triangle like ABC here, where we do not have the height given to us. We can still find the area under certain conditions. So the first thing that we're going to do is, even though we don't have one, we're going to draw in that altitude h, okay? And then we're going to write an equation using a trig ratio in terms of, and this particular time here they're putting us at angle C as a reference angle. We're going to write a trig ratio in terms of angle C, the height of ABC, and the length of one of its sides. So because all we really know is involving angle C and this h, we do not know this length from C to D because the A here is meant to be, just so you can kind of keep that in perspective, just like over on the left here, A is the length of the whole side CB. So we can't figure out what CD is, but we do know the length of B here, and we know H. So because of that, that's our opposite and our hypotenuse. And so we're going to write a trig ratio of sine of angle C is equal to h over b. Then we're going to solve that equation from step A for h. And to get h alone, we just multiply both sides by b. So we get that h equals b times the sine of C, angle C. Then what we're going to do is we're going to complete this formula for the area of triangle ABC in terms of h and another of its side lengths. So if we knew h and of course a is the base, we could say 1/2 base times height is actually 1/2 a times the height. Now, because we just solved for the height in another equation, we're going to substitute b sine C for h, and we get a new formula that is the area equals 1/2 little a times little b sine of big angle C. Now, keeping in mind what that was in the initial conditions of the problem, that was knowing this angle here, one side, and the other side. So that's two sides and the included angle. Really important to remember that. Two sides and the included angle. So that's under the conditions if we thought about our our congruence shortcuts, or how we would kind of label that triangle. That would be kind of like a side angle side situation to begin with. So if we continue and talk about reflecting here on this area formula, it says, does the area formula you found work if angle C is a right angle? So let's think about that. If angle C is a right angle, then this formula is really area equals 1/2 AB, and a right angle would be the sine of 90. Well, if we think about what the sine of 90 degrees is, if you do it on your calculator or you think about a 90-degree angle, you would have the opposite and the hypotenuse being the exact same length. So this piece right here, sine of 90, is just equal to 1. And so, yeah, it would be able to work if we had 1/2 AB sine 90, which is 1, because that would just be, move some space here, that would just be that the area equals 1/2 AB times 1, or 1/2 AB. And again, think of the picture that we would have there. If we took the triangle up top here, if we took the triangle up top here and we modified it so that this angle C was 90, then this B and A would be perpendicular. And so our picture would look kind of like this. This is my angle C, this is my little b, and this is my A. And then we'd have our triangle that looked like that. And then of course A and B would actually be the base and the height of the triangle. So that hopefully makes sense. Yes, that formula works even if C is a right angle. But most of the time when we use this, you guys, it won't be that C will be a right angle. So let's continue on to the next page. And as we look at explain 1 here, this is the area formula that we just derived in the Explore. So just keep in mind that this is used when you have the lengths of 2 sides and the included angle. Included, really important. So again, there's actually 3 different setups for the area in any one triangle. But specifically you would want to use the one that includes the 2 sides you're given and the included angle. So here's example 1, so we can kind of talk through this. Find the area of the triangle to the nearest tenth. So the known side lengths that we have are 3.2 and 4.7. We're going to call those little a and little b, which makes this angle 142 in the middle, angle big C. And so we're going to substitute into the area formula what we know. Area equals 1/2 AB sine C. So area equals 1/2, A is 3.2, B is 4.7, and then then angle C is the sine actually of angle 142 degrees. Make sure your calculator is in degree mode, and then honestly it's just evaluating it, crunching it in your calculator, and then make sure that you are rounding to whatever they asked you to round to. In this case the nearest tenth, so 1 decimal place. And we get an approximation. It won't be exact because we don't have the exact height, but it will be a very close approximation to the area. So in this case the area is 4.6 meters squared. Don't forget to add those units at the end in any area problem. As we move on to the next page, part B of the same idea here, finding the area of the triangle. This time we do not have a diagram that goes with it, so honestly you guys, it doesn't really even matter if you have the dimensions right really to begin with. I always just, if I don't have a diagram, I just sketch what looks like an equilateral triangle, and I put some measurements on, I put the labels on, D, E, F, that they're telling me this triangle is, and then I just put the measurements on. So I know that DE is 9, that DF is 13, and that the measure of angle D is 57 degrees. So I can see my side setup. I have an included angle A between 2 sides. So if I write it in terms of 1/2 AB sine C, here's my little a here, here's my little b, those are the 2 sides, and then this actually is kind of like my angle C from the previous page. So in terms of triangle DEF, the 2 included sides are DE and DF, and the included angle C from the previous one, even though we have new labels here, is the sine of angle D. So we have 1/2 DE we know is 9, DF is 13, and our included angle D is 57 degrees. That's a 7. Then we're going to evaluate with our calculator and just crunch the numbers. And in this case, make sure it's in degree mode, we get 49.1. And again, we have units that are inches squared. So take a pause in the video here before we move on to our next explain 2, and do these two your turn problems, 3 and 4, and then we'll move on. Okay, in Explain 2, we are doing what's called solving a right triangle. And anytime you're asked to solve a triangle, whether it's a right triangle or otherwise, we're going to be moving on to new types of triangles in the next video, non-right triangles. But to solve a right triangle, that means finding the lengths of all its sides and the measures of all its angles. So you're going to be given certain things to begin with, but you're going to need to find everything else that you don't yet know. That's what solving a right triangle means. So to solve a right triangle, you need to know two side lengths or one side length and an acute angle measure. And based on that information, we're going to figure out which trig ratios we want to use, whether we want to use inverse trig ratios, and whether we might need to use the Pythagorean theorem to help us figure out the rest of these things here. So for part A of this problem, looks like we're starting by finding the missing side BC. This is a word problem that talks about a shelf is coming out from a wall here, and it is extending 7 inches out from the wall, and we want to place a brace that we know is already purchased as 9 inches long, so that's the hypotenuse, under the shelf, and we want to know where exactly should we drill some holes in the wall here at point B. How far below will we need to make it? So to the nearest degree, we want to know what the angle is that the brace is going to make with the shelf, and we also want to know how long is this BC. So part A is helping us find BC, and that's just Pythagorean theorem. So we have AC here, side AC plus side BC, side AC squared plus side BC squared equals side AB squared. And substituting what we know, we have 7 squared plus our unknown equals 9 squared. BC squared then is 32 with some arithmetic, and to take our square root, we want to find it, remember, to the nearest tenth of an inch. It's going to be 5.7. Once we know that BC, go ahead and put that on the diagram, which is 5.7 inches. Then we want to find the other missing pieces of this triangle, which are angles A and angle B. In order to find an angle, you know we're always going to have to use the inverse. That's the second function trig buttons on your calculator, remember. So what we're going to do is we're going to find the lengths of what we already know to begin with. And I would always use not the rounding angle that you just got. The 5.7 is an approximation. Go back to what you had as actually given to you as exact to begin with. So if we sit ourselves here at angle A, then 7 is our adjacent and 9 is our hypotenuse. So adjacent over hypotenuse, that's why we're picking a cosine ratio here. So cosine of A is 7/9. Then we're going to find the measure of angle A as the inverse cosine of that 7/9. And in our calculators, and remember we're rounding to the nearest whole degree, that's going to be 39 degrees. Now, because I know that angle A and B in a right triangle here are complementary, we're going to substitute the measure of angle A plus the measure of angle B is 90, and substitute 39 that we just found for measure of angle A. Then we're going to subtract that 39 degrees from both sides, and we get that measure of angle B is 51. The question is it possible to find the measure of angle B here in our reflect number 5? Is it possible to find the measure of angle B before you find the measure of angle A? Well, let's think about that. Go back to your diagram. Let's redraw our diagram with what we had to begin with. We had our right angle here, we had 7, and we had 9. Here's angle B, and here's angle A. If we sit ourselves at angle B instead, to find angle B first, we would be going with 7 being our opposite, and 9 being our hypotenuse still. Hypotenuse doesn't change, right? But opposite and adjacent sometimes switch around depending on where you start yourself in the triangle. So what do you guys think? Can we find angle B first? I think so. With the diagram that we have here, absolutely we can find angle B first, but we wouldn't have used cosine to begin with. We would just use the sine of angle B instead. And then we do the same thing as we did before with substituting it into a complementary situation and subtracting it. So we would have found 51 first and then done the subtraction to find 39. Same exact outcomes no matter where you start in the triangle. So keep that in mind. It does not have to be, I don't know which angle to start with. Just pick one, use the ratio that makes sense with a given sides or given angle, and go from there. All right? Okay, on the next page, 727, doing some your turn problems here, 6, 7, and 8. So take a pause in the video and work through those problems. Okay, if you're done the your turns for explain 3, we're going to, or excuse me, your turns for explain 2, we're going to move on to explain 3. And that is solving a right triangle when that right triangle is located on the coordinate plane. So we're going to do the same thing for solving the triangle and remembering that that means we're finding all the missing pieces. But if it's plunked on a coordinate plane like this, sometimes it's a little easier to find distances. Particularly on this example that we're given to begin with, we can count some coordinates. So we know that AB from A to B is 4 units long. And from B to C is 7 units long. So use the distance formula or Pythagorean theorem, whichever, and you're going to find that the hypotenuse AC is the square root of 65, which is approximately 8.06. So I know, of course, that angle B is perpendicular because it's on the grid, but if I didn't know that, we would need to verify that those slopes of AB and BC, or whichever sides come together at that right angle, are opposite reciprocals, so we know that that's 90 degrees. Then we're going to use an inverse tangent ratio to find one of the angles. In this case, they're starting us with a measure of angle C, so we know that's the inverse tangent of 4 over 7, since those are the two sides that we're given. With respect to being here at angle C, we would have the opposite and the adjacent. So inverse tangent of 4/7 is approximately 30 degrees. And so since A and C are the complementary angles here, if we know 30, then we know the other by a quick subtraction is 60. Moving to the next page to do part B of solving a right triangle, right on the coordinate plane. This time we're not given the diagram, but we are given the points, so let's start by plotting those points. D is -4, 3. E is 3, 4. And F is right at the origin. So here is our triangle. Now we hope this is a right triangle because we're in the right triangle module of this book, but we're not really sure of that. So what we need to do is to check the slopes. So we're going to start by checking the slope of DF here. And we can do rise over run, or we can do the slope formula. Either way, the book uses the slope formula. So again, we're going to look at D and F. And we are going to look at subtracting 0 minus 3, and then 0 minus -4. And we get -3 over +4, or -3/4 for that slope. Then we need to check whether that is perpendicular to the other thing that we think is making that right angle at, or at least we hope is making the right angle at the origin at point F. We've checked DF, we now need to check EF, the slope there. And so EF's slope is, we're going to look for E and F here, 0 minus 4 over 0 minus 3. And that gives us a negative 4 on the top and a negative 3 on the bottom, so positive 4/3. If we remember about perpendicular slopes, these two right here are indeed opposite reciprocals, or we can think of the idea of product of the two slopes equals -1, whichever way you want to think about it. But yes, we have verified, just like in a quadrilateral, that the angle here is a 90-degree angle. So now that we know it's a 90-degree angle, we know we can use our SOHCAHTOA and we can use our trig ratios. But we need to find some lengths. So we're going to find the side lengths using the distance formula, or Pythagorean theorem, whichever. Book uses the distance formula to find DE first. So we're back here with D and E, just to kind of keep an eye on where we are. And that's going to be 3 minus -4 and 4 minus 3 all squared. Off to the side, if we were to think of what that is, that's 7 squared plus 1 squared under the radical. So that's the square root of 49 and 1, which is 50. Simplifying that out, we get that that's 5 radical 2. So I'm going to put that on the diagram. DE is now 5 radical 2. DF, if we were to find the distance there, D, make it black now, and F. So we're going to look for DF to be 0 minus -4 for our x's, and 0 minus 3. And so in that case, we have a 4 squared, and then plus a -3 squared under the radical. So 16 plus 9 is 25. And the square root of 25 is just a nice round 5. So DF has a length of 5 with our right angle in the middle here. Final length we need to find is EF, of course. And we'll go back to red here. We've got a star E and F. Okay, E and F. Distance is going to be 0 minus 3 and 0 minus 4 all squared. Off to the side, again, we'd have -3 squared in the first parenthesis and -4 squared in the second. Really doesn't matter whether it's negative or positive. When you square it, it still becomes positive. So positive 9 plus -4 squared is positive 16. We get 25 again, and oh look, we get 5. So now that we have all the distances, we need to find and solve for the angles. So we're going to use an inverse sine ratio. They're just starting us at angle D, but it really doesn't matter. If we're sitting here first, though, an inverse sine ratio, or you could use tangent or whatever. They're picking inverse sine, so we'll go with that. Measure of angle D, oops, lost my diagram. Measure of angle D is going to be EF, which is our opposite, over our hypotenuse, which is DE. And if we have the inverse sine of EF, which is, we know, 5, over DE, which is 5 radical 2, on our calculators there, just remember to put all of that 5 radical 2 into parentheses in the denominator. And when we do this correctly, we get 45 degrees there. Also, hopefully you guys are seeing the special right triangle 45, 45, 90 pattern here with 5, 5, and 5 radical 2. So we should have anticipated 45 degrees. Then we know that D and angle E are complementary. And so the measure of angle E is going to be 90 minus the 45, which is another 45 degrees. You only have one your turn here on this video, and that is on the next page, 729. So take a pause in the video and make sure you get this number 10, your turn, done for the next time. We'll see you next time.